Welcome to this demonstration of hypothesis testing for the difference of two population means. Here we're continuing in the context that we used previously as we were assessing whether the two population variances differed from one another. And again, the context of our example is Hamilton ACO, which is specifically interested in understanding spending among its dual and non-dual populations. Here I've written up the sample data that an analyst pulled for us, and we can look to see that on the surface, it looks as though the dually eligible beneficiaries have higher average spending at $12,413 relative to their non-dual counterparts. But before we can make that conclusion about the population, we need to first think about the amount of sampling variability. And you can see here from these descriptives that there's high variation, high dispersion in spending in both groups. So we want to take a step back and formally evaluate whether or not there's a difference in average spending between the dual and non-dual populations. To do that, we're going to use hypothesis testing. And so before I begin, let me make an assumption about the threshold or significance level that we're going to use. It establishes the criteria and the threshold at which we're willing to reject our null hypothesis in favor of the alternative. Let's take a look at the hypotheses, specifically when we're looking at two population tests. One thing you can see here is that when we are writing down hypotheses for the difference of two populations, most often the status quo, the null, will be expressed as no difference. And we write this as a linear combination to help us remember how to write down the test statistic. Specifically, in this case, I've written it down as the population mean spending for the duals minus the population mean spending for the non-duals is equal to 0. Whereas the alternative hypothesis is that that difference is not equal to 0. Now, this does not assume a priori a direction, whether one has higher average spending than another. If we had wanted to do that, we could have re-expressed this as a one-sided test, most likely as an upper one-sided test to reflect the fact that we can observe from our sample information that the duals do appear to have higher spending based on the sample. All right, let's proceed now to the test statistic. So remember that when we have unequal variances, which is the case here that we just showed previously, we need to use version 2 of the test, which assumes unequal variances. Our test statistic is going to have 3 parts. It's going to have a point estimate of the difference, which is just equal to x bar for the duals minus x bar for the non-duals. It is important here that the ordering that you use in the hypothesis holds here with the point estimate of the difference. The second term is the value under the null hypothesis. So that 0 is coming from this value right here. The null hypothesis is that there is no difference, and so that's what I'm going to insert into the numerator. The last piece of this is the standard error of the difference, which, as you know, can be a complicated calculation. Now, it turns out that version 2 has an easier calculation for the standard error relative to the version 1, where we have equal variances, but the complexity is made up for in the calculation of the degrees of freedom. So bear with me here. So let's write, first of all, the standard error formula. So it's going to be equal to the square root of the sample variance for duals divided by the sample size of duals plus the sample variance for non-duals divided by the sample size of non-duals. Okay, so I'm going to write this out just to try to make sure everything is clear. So we have $12,413 minus $8,762. That's the point estimate of the difference, minus 0. And then we're going to calculate out this denominator here. And I don't want to make any transcription errors, so we're going to have the square root of 21,939 squared divided by 493 plus 16,255 squared divided by 2,692. So when one crunches through all those numbers, you should get a test statistic of 3.522. Do expect some rounding error. That does happen depending on whether one is using decimals or whole numbers. And for the sake of simplicity here, I'm keeping things as whole numbers. All right, so the next piece of this, now that we have our test statistic, is we need to be able to identify our threshold or bar, okay? We're going to compare our test statistic to our critical values, which are going to be based upon the significance level that we have chosen. So here we're going to have, our test statistic follows a t-distribution, and you all are becoming experts in the t-distribution at this point. We have a two-sided hypothesis test, which means we're going to have two rejection regions, one in the upper tail and one in the lower tail. And because our significance level is 0.05, we're going to divide that in two, such that we're looking for the values on the t-distribution such that we have 0.025 in the upper tail and 0.025 in the lower tail. Now recall that a t-distribution in this case is going to depend on a particular degrees of freedom. And in version 2 of the hypothesis test, where we have unequal variances, we actually have to estimate those degrees of freedom using the approximation method. And you can tell here, given my limited board size, I'm not going to work through that approximation calculation. It's actually very complicated to do, but if one does work through it, and I did so this morning, then you will find that you get degrees of freedom, in this case, from the Satterwhite approximation. You get degrees of freedom equal to 594.8, or roughly 595 degrees of freedom. So we're going to use that information in addition to our significance level to arrive at our critical values. And again, in Excel, we can use our t.inv function to be able to identify those particular critical values. And in fact, here, we will find that for those values, for those degrees of freedom and alpha, we will find our lower critical value to be minus 1.964 and our upper critical value to be positive 1.964. All right, so the last piece of this, of course, is to compare our test statistic with our critical values. And our test statistic specifically kind of sits out here at 3.522. You can see on this that that is more extreme than our upper critical value of 1.964. And given this, that is telling us that we have evidence to reject the null hypothesis in favor of the alternative. So we can conclude that the population mean spending for the dually eligible population is different from that of the non-dual eligible population. Now, the last thing I promised you was to talk a little bit about what would happen if we did a one-sided test instead of a two-sided test. Specifically, in this instance, we would have a different expression for our null and alternative hypotheses. However, the test statistic would remain the same. The one other thing that would change in our calculation is that instead of having two rejection regions, one in the upper and one in the lower tail, we would have only one rejection region. If, for example, we had written this as an upper one-sided test, our rejection region would have sat in the upper tail of this distribution. If we had held everything else constant, that upper critical value where we have 0.05 in that upper tail, that critical value would be approximately 2.34. And so we would still have evidence in that case, given our test statistic value, to reject the null in favor of the alternative. You can see that most of the structure remains the same, but we do have to be careful about those pieces of the problem that shift when we change the particular type of hypothesis we want to assess. This concludes our example of hypothesis testing for the difference of two population means. Thank you.